Thank you, organizers, for inviting me to speak among such eminent speakers. And I would like to share with all of you today the advancement in two-photon imaging towards the non-invasive imaging in humans. With such a large progress in developing therapies against the retinal diseases, it becomes even more important now that we have the imaging modalities that could interrogate biological processes as they occur in the living eye. So we can detect the ensuing pathology, or we can track the impact of the therapy at the earliest possible stage. There was also a huge progress in the imaging techniques that now, even with the adaptive optics, can visualize individual photoreceptors, or like in the OCT, where latest improvements with including OCT angiography without any dye provide us not only with the section of the retina in vivo, but also with the map of the vasculature. However, neither of this technique can access fluorophores, that endogenous fluorophores, that participate in the biological processes. And the reason for it is that they have excitation spectra in the UV region. And this region of light is very harmful to the eye. That is why we are using two-photon excitation to image the retina and RPE in the living animal. And here you have the RPE with the retinal ester containing retinosomes around the border of the RPE, and the black nuclei are in the center. Another example of using this technology provides us with the 3D volumes of the RPE and how it is intercepting with the photoreceptors in the healthy mouse, like bulb C, where on top of the images are the RPE cells with black nuclei and the retinal ester or retinosome particles around the borders. And then we see the forest of photoreceptors that are highly distinguishable with this magnification of the image. However, in the other model, mouse model of MERTK knockout mice that have defective phagocytosis, already immediately under RPE, you can see the defective photoreceptors, they are enlarged. And if we go a little bit deeper, towards the inner retina, we can see the multitude of the macrophages. Another advancement in this technology, in two-photon excitation, is that we could visualize multiple fluorophores, which are distinguished by the fluorescence lifetime imaging. And both those images are obtained based on the endogenous fluorophores, and this is RPE65 knockout mouse that has a blockade of the retinoid cycle. And the fluorophores in the RPE in that mouse are mostly retinal esters, and the fluorescence lifetime are quite long. Whereas in the different model, the PV-PV knock-in model, we see the multitude of different fluorophores in the RPE that could be distinguished by the very different fluorescence lifetime, ranging from shorter than 0.4 nanosecond to longer than 2.7 nanosecond. And we know that the shorter fluorescence lifetime corresponds to such a retinal condensation product. And the longer one are similar like in the RPE65, which is retinal esters. Furthermore, we can visualize the entire volume of the retina. And here on the left is the ABCA4 RDH knockout, which we call the double knockout. And we see the images here and pass as the sectioning goes all the way from the RPE to the ganglion cell layer. To obtain this section in the wild-type mouse, we have to obviously increase the laser power to the limit that it will not be safe to image in humans. To visualize the details of the photoreceptors and RPE interdigitation, we have injected the mice or injected the mouse eye with the PNA conjugated with the fluorescein. And here are the pedicles, then we see inner plexiform layer and the details of the ganglion cell layer and the vasculature there. The other way to employ the two-photon microscopy is to look at the pathological processes. And here we use the double knockout mouse, which is a model of light-induced retinopathy. And after exposure of this mouse to 10,000 lux for 60 minutes, we look with the two-photon microscopy at the different time points. And upper level shows the images of the outer segment just beneath the RPE, and lower level in images of the RPE as a function of time after exposure to light. In the outer segment layer, again, before the exposure to light, with this, we don't see the individual photoreceptors, even though we know they are there and we can see them with the larger light. However, already 1 day after exposure to light, we see enlarged photoreceptors, and fluorescence is increasing. On the third day after exposure to light, there is a larger quantity of these enlarged photoreceptors. And furthermore, we also see macrophages invading that space and trying to clear out the space from the sick photoreceptors. When we look 11 days after exposure to light, we don't see anymore neither the macrophages or we don't see enlarged photoreceptors. When we look a little bit deeper, we will see the macrophages that now have the ramified shape. When we look at the RPE of this mouse, 1 day after the exposure, we see that the retinal esters in the retinosomes are starting to show up around the border. And at the 3 days, the image is about the same. However, 11 days after exposure, we see the bright spots in the RPE, and they are randomly distributed towards the layer. So we thought that we could use this knowing what's happening in the RPE and outer segments after exposure to light. We can use maybe this method to see what is happening after treating the mice with drugs. And here are drugs and the impact on retina protection. And the drugs have a very different mechanism of action. And here is retinolamine that Philip was just talking about. And here is aposinin, which is NADPH oxidase inhibitor. And here are 2-hour control. And in both mice that were treated with drug, with retinolamine and with aposinin, the RPE is preserved, and we don't see both. We can see this both with 730 and with 850 nanometer. When we don't treat the mouse but still exposed to light, we see that with 730 and with 850 nanometers, we have those spots that are distributed randomly towards the RPE. And because they are visualized with both of these wavelengths, we confirm also through other biochemical methods that those are all transretinal condensation product. And here is just the quantification. Another types of drug that we were looking with that technology and that Chris is inventing are the drugs acting on G protein coupled receptors. And here we look at the 2 different combinations of drugs. And control is the DMSO. And again, this is a very low magnification picture, but this is a section, this is the imaging section through the eye. So this would be the RPE cells, and the center of this picture is filled with the dying photoreceptor. And both of this drug combination were preserving both the RPE and the photoreceptors. And here is the higher magnification picture for all these drugs, how they are effective. However, to use this technique to image, to apply to humans, we need to reduce the laser power to the levels that are safe and do not introduce any effects that are undesirable. So to do that, we had to look with greater accuracy at what's really happened during this two-photon excitation. And the process was described quite a while ago by Maria Goppert-Mayer in her Ph.D. dissertation, and here she is riding a bicycle with Niels Bohr. However, practical implementation of this two-photon excitation had to wait quite long, about 40 years, for the invention of the new pulsing lasers. So in the pulsing lasers, the laser pulse comes at about 80 megahertz frequency, so they are separating by 12.5 nanoseconds. That's a current state of the art of the laser. And if one works out the equation, the fluorescence is inversely proportional to the duration of these pulses and inversely proportional to the frequency that the pulses are coming with. However, the short pulses have the inherent wide bandwidth. And unfortunately, most of the materials have the refractive index that is changing with the wavelength. And because of that, pulses that have wide bandwidth the different spectral components will travel with different speed through the optical system. So then they will arrive at the sample, or in our case, at the eye, that they could arrive even longer than when we started significantly. Thus, we have developed or incorporated the new dispersion compensation process. So it means that we are slowing down the red, the longer wavelength, and speeding up the blue, so they arrived at the sample at the same rate. And indeed, we measured that with such a dispersion compensation, the pulses as measured in the sample arrive at the same time. How it is working? That the laser light is put on the diffraction grating, which splits the light into the individual spectral components, and then the individual spectral components are modulated by spatial light modulator, such that their phases are just adjusted and that they arrive at the same time at the sample. And here is the data. To understand what we are seeing in different mouse models of the retinal diseases, we also look at the excitation spectra coming from the double knockout mice and from the RPE 65. And one could see that with increasing the excitation wavelength, we see the rapid decrease in the fluorescence coming from the RPE 65, and double knockout mouse is less sensitive. The spectral shape of the pulses that we were using to elucidate the fluorescence was here like that. So for the 20 femtosecond, which I will be using throughout this paper, we had the more energy towards the shorter wavelength. So now we can understand what is happening here. The blue line is theoretical, that Maria Goppertmeyer was predicting, and here how our fluorescence should grow. In RPE 65, the fluorescence is growing faster because we also take advantage of the higher bandwidth being at the shorter portion of the wavelength. And we see this increase in the RPE 65. Here we run the trace through the retinosomes, through the RPE cells, and we see that the increase is, depending on the area, is on the range of about 3. And in some areas, we don't really detect any fluorescence or any retinosomes with the 75, but we detect with 20 femtoseconds. And it's the same story when we look at the mouse model of light-induced degeneration. But what does this mean really for the imaging in humans? So here we decided to look at 1 milliwatt at 790 nanometers and looking at collecting 120 imaging frames. And this exposure corresponds to 28% maximum permissible per NZ. So we would expect that with this exposure, we should not be damaging or causing any alterations to the human retina. And we obtained these images. So these large images are the images that were obtained, aligned, and averaged after collection of 100 imaging frames. And this is with each of these lasers, 75, 32, and 20 femtoseconds. And clear features of the RPE could be visible for both 20 femtosecond and 32 femtosecond laser. However, only the very, very abstracted outline of the RPE is visible here. And insets are showing the images that were obtained from the averaging of 50 frames. This averaging and alignment is extremely important because during 100 seconds of the imaging, the mouse would be breathing and the heart will be beating, that there will be some movement in these images. All right. However, one caveat with the safety recommended by the American National Standard Institute is, if you look very, very carefully through this thick book, it says that for pulses that are shorter than 100 femtosecond, there is a lack of biological data. So we should use the recommendation for the pulses that are shorter than 100 femtosecond. So really it is up to the researchers to really prove that those are safe. So here to assess the safety, we use the in vivo test, and on the left are the scanning laser ophthalmoscopy images in bulb C, albino double knockout, and pigmented double knockout. And here are the OCT images. And mice were exposed to either white light, to imaging light for 120 seconds, or were not exposed to no light. So shortly, we see that there is no impact of the imaging for 120 seconds on the structure of the retina. And we confirm this also by the histology and by the functional measurements. By the ERG measurements, there were no significant differences between mice that were not exposed to light and were exposed to the infrared light for the imaging conditions. Another way that we have the capability in the lab is to measure the rhodopsin content, as well as 11 cis retinal, because they both represent functioning visual cycle and functioning retinoid cycle, which is representative of the integrity of the retina. And here again, we don't see any differences between mice that were exposed to infrared used during the imaging or were not exposed to light. However, both the white light was causing the damage in all the genotype that we used here. And here we use glial fibrally acidic protein to look at the gliosis. And we saw the prevalent gliosis in the albino double knockout mice after exposure to white light. However, no gliosis again was detected in either no light or infrared, or mice that were exposed to infrared light. Thus, we confirmed the increasing 2-photon fluorescence signal by reducing pulse duration does not introduce any damage to the retina. What are the other opportunities? So the other parameter here is pulse repetition frequency, and here we incorporated pulse picker, which it is a device that lets only the particular pulses through the system. And we expect that the fluorescence for the same laser power will be increased inversely with the pulse repetition frequency. And here is our first image, that is work in progress, that we obtained with 1 megahertz, 790 nanometer, and at this point the acquisition time was only 1.2 seconds, and the power was 0.3 milliwatt. So obviously we need to follow this with assessing the safety of this repetition frequency and perform more tests with a different repetition frequency, as the pulse picker is capable of delivering us from 2 to about 1,000 degrees. So if we have right now 80 megahertz, we should be able to go with less than 1 megahertz. So in summary, the harnessing 2-photon excitation of retinal fluorophores provides 3D visualization of individual retinal layers and the interconnections, insight into the steps leading to retinal degeneration, and assessment of the potential of pharmaceuticals to protect the retina. Reducing laser pulse duration and pulse repetition frequency enables rapid imaging with low laser power needed for imaging human eyes. And I would like to thank the institutions that made this research possible, as well as my collaborators, which most of them are here in the lab, however, and in the symposium. That will be Chris, who instigated this project, Yu-Chen, Elliot Choi, Chi-Chen, Philip Kaiser, Akiko Maeda, David Salon, Avery Sears, Patrycjusz Stremplewski, Suzy Su, Maciej Wojtkowski, and Gianni Jerzak. Right, so my understanding is that the patient is able or is willing to put about 2 to 3 minutes for this kind of imaging. So our goal would be to get below that time. Maybe there is the imaging that were shown previously with other group. They were using about even lower imaging powers. However, for this you need about 20 minutes, which appears a little bit excessive for the normal humans, for the settings. That's right. And every of these additional hardware devices, like eye tracking, requires their own light source. Whereas, for instance, the typical way to do it is to use the reflective light to track eye in the real time. So it increases the complexity. It is possible. However, everything is then a little bit more expensive, a little bit more complicated.
Okay, thank you very much.